Hi there, welcome to lecture 28 of Fox, the last lecture. Okay, so let's have some fun discussing efficiency. Okay, we're going to talk about the class P, polynomial, the class NP, which is not non-polynomial. It stands for nondeterministic polynomial. Wow, fancy words. Okay, and then we'll touch on this famous concept called NP completeness. Okay, now, before we get going, let's have a quick recap of last lecture, because that was the punchline of the course, the blockbuster lecture on the theory of computing. So we introduced this Turing machine, okay? And it turns out it's a very powerful machine. In fact, a Turing machine can be constructed, which we call the universal Turing machine, that can simulate any other Turing machine. So it takes that Turing machine's description as input together with, a string W, and then simulates the operation of this Turing machine M on the input W. Okay. Now, the moment you're able to construct such a powerful universal Turing machine, it actually opens the door to very many unsolvable problems. And what we discussed last time was that, certain problems like, the domino puzzle, the ultimate debugger or the halting problem, the program verifier, none of these problems can be solved. And no, in this case, means no. It's not that I can't solve it. It's not that you can't solve it. It's not that the Martian can't solve it. It cannot be solved on a Turing machine. Okay. And so we have this notion of what is solvable. What is a computing problem that's solvable, is a decidable computing problem, and a decider, a Turing machine that always halts and outputs yes or no, captures the intuitive notion of an algorithm. So that completes our discussion on what can and what cannot be computed. Our model of computing is a Turing machine, okay, a decider, a Turing machine that always halts. That's what we mean when we say we have an algorithm. Okay. And then a problem is a language, a set of finite binary strings. Okay. And the goal of an algorithm is to take an input and say yes or no, does it belong to your set? Okay. And if a particular language or a particular computing problem can be solved by a decider, then that problem is solvable, and we say that it's computable. Okay. But then there are problems which we prove that are not solvable, so those are not computable. So it's a little bit depressing that there are all these great problems that we cannot solve. But in some sense, we might have expected it. We can't solve everything, okay? And so what's the path forward? The path forward is to focus on the problems we can solve, on the decidable problems. And so I'm just going to give you a little bit of a tour through a typical curriculum in CS, and of course, we begin at Fox. Okay? And what did we learn in Fox? So we started with discrete math, but then we talked about the theory of computing. And what was the theory of computing? Well, we started simple. We defined what's a computing problem, but then we started simple with the DFA, which is regular expressions, which can solve regular expressions. We talked about context-free grammars and parsing, and then we ultimately came to the Turing machine. Okay. Now, in discrete math, we talked about a lot of stuff. We talked about proof techniques, recursion, sums, number theory, graphs, counting probability. So that's basic discrete math, and we use some of that in the theory of computing. There is other math, like graph theory, linear algebra, probability theory, multivariate calculus. There's a whole bunch of math that's useful in computer science. Okay, now that we have all that, let's say math and the theory of computing, where can we go from the theory of computing? Well, as I said, we now should start focusing on what we can solve now that we understand what we cannot solve, what's unsolvable. Okay, and really, this means that we need to focus on not just what we can solve, but how quickly can we solve them. So now the next issue becomes how quickly can we solve them? Can we solve them fast, i.e. polynomial? Can we not solve them fast, i.e. it requires exponential time? It turns out that there's a fuzzy boundary between fast and not fast. Okay, and that's related to this concept called NP. Okay, so studying efficiency would sort of be the next step in the theory of computing, and if you really want to understand these concepts of P, NP completeness, read chapters 28 and 29. Okay. Now, in terms of courses where you would go from sort of a Fox-like theory of computing, you might take a computability and complexity course, to study in more detail what is computable, and complexity means how quickly can we compute those things that are computable. And you will indeed take a course in some kind of intro to algorithms course. Okay, fantastic. Okay. But in general, we can sort of break computer science into sort of two big parts. The purple part here is theory, algorithms, and AI, and there's a lot of stuff there. Okay, there's this the theory of computing, algorithms, and there are all kinds of algorithms: approximation, randomized, distributed. There are applications to cryptography, to data like machine learning, vision, graphics, finance, okay, to networks. Okay, Okay, computers, social networks, data networks like the internet, robotics, security, programming languages, program analysis. There's a lot of theory and algorithms that's going on in this purple bucket. Okay, and all the math that you learned and the theory of computing comes to play in that bucket. So if you're interested in theory, algorithms, AI, there's a lot of, there are a lot of paths to move forward, and there's a lot of stuff that will be used. Okay. On the other hand, you might be interested in software and systems, and it depends on what part of software and systems you're interested in. Are you interested in the sort of program analysis, programming languages, networks, robotics, security side, or are you interested more in developing systems like database systems, parallel computing, operating systems, architecture, and so on and so forth? Depending on what your flavor of software and systems is, you'll make use of grammars, DFAs, all the various kinds of math, induction, recursion, graphs, probability, and so on and so forth. So in some sense, you can't really escape the foundational math and the foundational theory of computing. It is really embedded into the rest of the curriculum. Now, depending on what your flavor is, you might emphasize, one over another. You might emphasize theory and math over software and systems. So that's, sort of a high-level view of where you can go from Fox. Now, where are we going to go in the rest of Fox? Well, we're just going to spend a little bit of time talking about efficiency, something that you will focus on much more in your next algorithms course. A little bit of time focusing on efficiency, but I really want to end on a note, an emphatic note. You'll have to stay tuned for that emphatic note. Okay. So, for the moment, let's go to the board and discuss a little bit efficiency.